This session, let's discuss assignment LCD 2. You can look at the first question. Limit x tending to 0, x tan 2x minus 2x tan x divided by 1 minus cos 2x whole square. 1 minus cos 2x whole square. Now, when you look at this question, you can see a standard limit extending to 0, 1 minus cos ax by x square. We all know through the discussion, limit extending to 0, 1 minus cos ax by x square is a square by 2. So, directly let us use this result here. Limit extending to 0, 1 minus cos ax by x square is a square by 2. So, 1 minus cos ax, we can replace it by a square x square by 2 whole square, that makes it 4, and 4 let us write it outside the limit. And we have in place of a in this particular question 1 minus cos 2x. So, this will also be 2 square 4 and 4 square is 16, 4 by 16 is 1 by 4. And x square whole square, we can see it as x power 4. Now, you can see one x common in the numerator, it gets cancelled with one x in the denominator. Now, our question is tan 2x minus 2 tan x divided by x cube. Tan 2x all of us know, 2 tan x by 1 minus tan square x. Now, let us simplify this question. This limit is 1 by 4, limit extending to 0. Tan 2x, we will write it as 2 tan x by 1 minus tan square x, and 2 tan x can be taken common from the numerator. 2 tan x by, I will lend one x from the denominator to 2 tan x into, we are left with 1 by 1 minus tan square x minus 1 divided by x square. Now, we all know tan x by x as x tends to 0 is 1. So, we can replace tan x by x with 1. Now, simplify, take LCM, 1 and 1 gets cancelled, minus of minus tan square x is tan square x. We have the limit to be 1 by 4, limit extending to 0, 2 we can take it out of the limit and 2 cancels with 1 by 4, makes it 1 by 2. 1 and 1 got cancelled, we have tan square x in the numerator divided by x square into 1 by 1 minus tan square x. Now, you can all see as x tends to 0, tan x by x is 1. So, tan square x by x square will also be 1. This limit, it would be 1. And as x tends to 0, tan x tends to 0. So, 1 by 1 minus tan square x is also 1. So, effectively our answer would be half, or the right option is C. If limit extending to 5, x power lambda minus 5 power lambda, x power lambda minus 5 power lambda divided by x minus 5 is given to be 500, then we are asked for positive values of lambda. If limit extending to 5, x power lambda minus 5 power lambda divided by x minus 5 is 500, we have to find the positive values of lambda. Now, this question is in a standard format of limit extending to a, x power n minus a power n divided by x minus a, and we all know the answer, it will be na power n minus 1. So, for this question, the limit is going to be lambda, a is 5 here, power lambda minus 1, and this is given to be 500. Now 500, let us prime factorize it. 500 is 125 into 4, and 125 is 5 cube into 4 is, let us write it as 4. Now we have 5 power lambda minus 1 into lambda given to be equal to 5 power 3 into 4. From this equation you can directly see that lambda equal to 4 satisfies the given equation. So lambda, it has to be 4, or among the options it's B. Next question, let f of x is equal to x if x is less than 0, 1 if x is equal to 0, x square if x is greater than 0, and we have to find limit extending to 0 f of x. So function is given, f of x is equal to x if x is less than 0, 1 if x is equal to 0, and x square when x is greater than 0. And we are asked to evaluate limit extending to 0 f of x. Now we know limit extending to 0 f of x exists only when left hand limit exists, right hand limit exists, and both of them are same. So let us evaluate limit extending to 0 minus f of x separately. Limit extending to 0 minus left hand limit, x is slightly less than 0, and whenever x is slightly less than 0, f of x is defined as x. So this is limit extending to 0 minus x, which is 0. So left hand limit we can see it is 0. And let us look at right hand limit. Limit extending to 0 plus f of x, that means we have to evaluate the limit when x is slightly greater than 0. So when x is slightly greater than 0, f of x is defined as x square. F of x is defined as x square. So this is limit extending to 0 plus x square, or simply 0 again. So our answer, because limit extending to 0 minus and limit extending to 0 plus are same and both of them equal to 0, answer would be 0. So limit extending to 0, f of x is equal to 0, it's option A. Answer is option A. Next question, limit extending to 0, x cos x minus log of 1 plus x divided by x square is equal to, we have to evaluate limit extending to 0, x cos x minus log of 1 plus x divided by x square. Now to evaluate this question, we can go for several approaches, one of which is L'Hospital rule. You can differentiate numerator, differentiate denominator. As x tends to 0, x cos x is 0, log 1 is also 0, x square is also 0. So it's a 0 by 0 form, and we can see all differentiable functions here. So this limit will be same as limit extending to 0, denominator derivative is 2x, numerator apply UV rule, derivative of x cos x is cos x plus x into derivative of cos x, which is minus sin x, minus derivative of log of 1 plus x is 1 by 1 plus x. So the question is limit extending to 0, cos x minus x sin x minus 1 by 1 plus x divided by 2x. Now let us see what this limit is going to be. Limit extending to 0, x sin x by 2x, we can separate it out, cos x minus 1 by 1 plus x divided by 2x minus x sin x divided by 2x. Now x and x, you can see it gets cancelled, and as x tends to 0, sin x also tends to 0. So limit extending to 0, x sin x by 2x is 0. Now let us evaluate the next part. This limit we can write it as limit extending to 0, take LCM, cos x minus 1 plus x cos x divided by 2x. Now again we can split this limit into two parts, cos x minus 1 by x and x cos x by x. So this limit can now be written as limit extending to 0 cos x minus 1 by 2x plus limit extending to 0 x cos x by 2x. We know limit extending to 0 cos x minus 1 by x square is minus half. So because we have only x here, multiplying and dividing by x, this is a non-zero finite number multiplied by some number tending to 0, this limit is going to be 0. So we are only left with a small limit, limit extending to 0 x cos x by 2x, x and x gets cancelled, and as x tends to 0 cos x is 1, so this limit is going to be half. So our answer is half, that is option A. Limit extending to 0 modulus of x plus 1 plus modulus of x minus 1 minus 2 divided by x. We have to evaluate limit extending to 0 modulus of x plus 1 plus modulus of x minus 1 minus 2 divided by x. Now we all know the definition of mod x. Mod x is x whenever x is positive and mod x is minus x whenever x is negative. So whenever we are dealing with mod, we need to investigate whether the quantity within the modulus is positive or negative. If it is positive, we can simply remove the modulus sign, and if it is negative, we have to put a minus sign and remove the modulus sign. Now x is tending to 0, limit x is tending to 0. That means x is in the vicinity of 0. X plus 1 will be around 1, and this quantity will always be positive. Any quantity close to 1 is positive. So we can remove the modulus sign. Mod x plus 1 will be x plus 1 itself. Then we have mod x minus 1, and because x is around 0, x minus 1 will be close to minus 1, which is negative. So modulus of x minus 1 will be 1 minus x. Now we can see x and x getting cancelled, 2 and 2 getting cancelled. So we are left with only 0 in the numerator, and 0 divided by whatever becomes 0. So answer will be 0, which is option D. Next question. Find the left hand derivative of f of x is equal to step x into sine of pi x at x is equal to k, where k is an integer. We have to find left hand derivative of the function f of x is equal to integral part of x or step x into sine pi x at x is equal to k, where k is an integer. At x is equal to k, where k is an integer. So left hand derivative, we know the definition, limit extending to 0 minus f of, at which number we are evaluating, at k, k plus x minus f of k divided by x. Left hand derivative will be limit extending to 0 minus f of, at which point we are evaluating, at k, k plus x minus f of k divided by x. This will be left hand derivative at k. Now f of k is, k is an integer, so integral part of k will be k itself, and sine pi k, sine of a multiple of pi, will be 0. So f of k is 0. f of k plus x is integral part of k plus x into sine of pi into k plus x, that is pi k plus pi x divided by x. Now we have to evaluate limit extending to 0 minus integral part of k plus x into sine of pi into k plus pi into x divided by x. Now let us see what will be sine n pi plus theta. Sine n pi plus theta. If you have a even multiple of pi, sine of even multiple of pi plus theta falls in first quadrant, so it will be sine theta, and sine of odd multiple of pi plus theta falls in third quadrant, it will be minus sine theta. So this will be plus sine pi x or minus sine pi x depending on whether k is even or odd. If k is even, this will be sine pi x. If k is odd, this will be minus sine pi x. So we can write it as minus 1 power k. Minus 1 power k is a number which is 1 when k is even and minus 1 when k is odd. Minus 1 power k into limit extending to 0 integral part of k plus x sine pi x divided by x. Now as extends to 0, sine ax by x is a. So this limit will be equal to pi. So sine pi x by x we can remove and replace it with pi, and pi we can bring it out of the limit. Limit extending to 0 minus k plus x. Now x is slightly smaller than 0, x is tending to 0 minus. So k plus x will be smaller than k. To k we are adding a small negative number that makes it smaller than k. So integral part of a number which is slightly smaller than k would be k minus 1. So answer for us would be minus 1 power k into pi into integral part of this as extends to 0 minus is k minus 1. So answer is minus 1 power k into k minus 1 into pi, which is option A. Next question. Limit extending to 0, a power tan x minus a power sin x divided by tan x minus sin x. We have to evaluate limit extending to 0, a power tan x minus a power sin x divided by tan x minus sin x. And it is also given in the question that a is greater than 0. A is a positive quantity. Now, this question is based on two simple limits. Understand as x tends to 0, tan x will tend to 0, sin x tends to 0, so the difference tan x minus sin x tends to 0. And also, a power tan x tends to 1 and a power sin x also tends to 1. Numerator, the difference tends to 0. So it's a 0 by 0 form. Either we can apply L'Hospital rule or we can even do it without L'Hospital rule. So in this question, let us do it without L'Hospital rule. Let me take a power sin x common from the numerator. So this will become a power sin x into, when I take a power sin x common from the numerator, this will be a power tan x divided by a power sin x or a power tan x minus sin x minus this a power sin x we have taken it common, so we will be left with 1 divided by tan x minus sin x. Now as x tends to 0, because sin x tends to 0, a power sin x will be 1. A power, a quantity tending to 0 where a is positive, will always approach to 1. So a power sin x we can replace it with 1. So this becomes limit extending to 0, a power tan x minus sin x minus 1 divided by tan x minus sin x. Now I can see tan x minus sin x as a single quantity tending to 0. Now this limit is in the form some quantity tending to 0, let's say y, y tending to 0 a power y minus 1 divided by y. This is a standard limit. Limit y tending to 0 a power y minus 1 divided by y. We all know it is log a. So, this is in the same form. As x tends to 0, tan x minus sin x also tends to 0. So, a power a quantity tending to 0 minus 1 by the same quantity, this limit will be log a. So, answer is log a, which is option B. Limit n tending to infinity 1 plus e power 1 by n plus e power 2 by n plus so on up to e power n minus 1 by n whole divided by n. We have to evaluate limit n tending to infinity 1 plus e power 1 by n plus e power 2 by n so on up to e power n minus 1 by n divided by n. Now, to evaluate this question, we can do this question in numerous ways, one of which is understand as n tends to infinity 1 by n tends to 0. Understand as n tends to infinity 1 by n tends to 0. And also, if you look at this expansion, this is 1 plus some x plus x square so on up to x power n minus 1. We can see a geometric progression here. 1 plus some number, let us say x plus x square so on up to x power n minus 1. So, let us use the formula of geometric progression here and write this expansion as limit n tending to infinity a plus ar square so on up to ar power n minus 1 will be a into a is first term in the geometric progression, which is 1 here. R common ratio is e power 1 by n. Power number of terms is n minus 1 divided by r minus 1. So, numerator it is equal to e power 1 by n whole power n minus 1 divided by r minus 1, which is e power 1 by n minus 1, and we also have this 1 by n. So, let us write it separately here. Now, let us see e power 1 by n whole power n is e and this number is e minus 1. A non-zero finite number, we can always bring it out of the limit. Now, this 1 by n, let us write it here as n tends to infinity 1 by n tends to 0. 1 by n tends to 0. So, this limit is equivalent as 1 by n, let me replace by x. As n tends to infinity, x tends to 0. I can replace 1 by n by x. It is limit extending to 0 x by e power x minus 1. We know this is a standard limit, limit extending to 0 e power x minus 1 by x is 1. So, its reciprocal will also be 1. So, we are left with answer e minus 1. This limit will be e minus 1, which is option C. Next question, limit extending to 0 sine of pi cos square x divided by x square. We have to evaluate limit extending to 0 sine of pi cos square x divided by x square. Now, let us see how to evaluate this limit. As x tends to 0, cos square x tends to 1. As x tends to 0, cos square x tends to 1 and pi into cos square x tends to pi and sin pi is 0. So, this is 0 by 0 form. Instead of using L'Hospital rule here, we can evaluate it directly, but for that we can see as x tends to 0, pi cos square x tends to pi. It would be more comfortable if we make this tend to 0. As x tends to 0, pi cos square x tends to pi, but evaluation would be more simpler if we make this tend to 0. For that, let us use a property from trigonometry. Sin theta is same as sin pi minus theta. Sin pi minus theta is same as sin theta. So, we can write this as sin of pi minus pi cos square x divided by x square. This limit can be written as limit extending to 0 sin of pi minus pi cos square x divided by x square. Now, as x tends to 0, this quantity tends to 0. Sin of any number tending to 0 can be equivalently written as that number sin x is equivalent to x. So, as pi minus pi cos square x is tending to 0, sin of pi minus pi cos square x, we can replace it by simple pi minus pi cos square x. And we can also take this pi common. Because it is a non-zero finite number, we can write it outside the limit. 1 minus cos square x is 1 minus cos x into 1 plus cos x. As x tends to 0, 1 plus cos x is 2. As x tends to 0, cos x is 1, 1 plus cos x is 2. So, I can separate the side and write it outside 2. And 1 minus cos x by x square, we know it is a standard limit 1 by 2. 1 minus cos ax by x square is a square by 2. So, 1 minus cos x by x square is half. So, this half and 2 gets cancelled and we are left with answer pi. So, it's option B. Answer is pi. Next question. Limit extending to minus 1 plus root pi minus root cos inverse x divided by root x plus 1. We are supposed to evaluate limit extending to minus 1 plus root pi minus root over cos inverse x divided by root x plus 1. Again, to evaluate this limit, we can approach in numerous ways. Before that, let us understand what this limit is all about. As x tends to minus 1 plus, x plus 1 would be 0 and x is slightly greater than minus 1. So, x plus 1 will be slightly greater than 0. So, there is no problem with the domain of this. Had it been limit extending to minus 1 minus, x plus 1 would be 0 but slightly less than 0, and because the quantity under root cannot be less than 0, answer would be does not exist. But here as x tends to minus 1 plus, we have x plus 1 to be slightly greater than 0. So, there is no problem with the domain of the definition. And x tends to minus 1 plus, x is slightly greater than minus 1, cos inverse of a number slightly greater than minus 1 would be tending to pi. So, root pi minus root pi is also 0. So, it is a 0 by 0 form. We can go for L'Hospital rule, but with the roots and all in place, differentiation would be comparatively difficult. So, let us simplify the question before we go for L'Hospital rule. So, this limit can be written as limit extending to minus 1 plus, let us rationalize the numerator, a minus b multiplied by a plus b. I will multiply numerator and denominator by root pi plus root over cos inverse x. So, it will be a minus b into a plus b, a square minus b square, pi minus cos inverse x divided by root x plus 1. So, as x tends to minus 1 plus, cos inverse x tends to pi, root pi plus root pi is 2 root pi, and 1 by 2 root pi we can bring it out of the limit. Because it is a non-zero finite number, we can bring this out of the limit and it is 1 by 2 root pi. Now, question is rather simpler. Limit extending to minus 1 plus pi minus cos inverse x divided by root x plus 1. Let us apply L'Hospital rule now. Limit extending to minus 1 plus, differentiate numerator, derivative of pi is 0, Derivative of cos inverse x is 1 by root over 1 minus x square with a minus sign, and that minus sign and this minus sign gets cancelled. Derivative of root x plus 1 in the denominator is 1 by 2 root x plus 1. So, we can write it as 2 root x plus 1 in the numerator. And we can see root x plus 1 here and root x plus 1 here gets cancelled. So, we are left with 1 by 2 root pi limit x tending to minus 1 plus 2 by root over 1 minus x. 1 minus x square, we are simplifying it as 1 minus x into 1 plus x. Root 1 plus x, root 1 plus x gets cancelled. We are left with 2 by 1 minus x. And x tends to minus 1. So, 1 minus minus 1 will be 2. So, this will be root 2. And from 2 by root 2 is root 2. So, our answer is 1 by root 2 into root pi, or 1 by root 2 pi, which is option B. Next question. Let f maps R to R be such that f of 1 is equal to 3 and f dash 1 is equal to 6. Then we have to evaluate limit extending to 0 f of 1 plus x divided by f of 1 whole power 1 by x. So, in the question it is given f of 1 is 3, f dash 1 is 6, and we are asked to evaluate limit extending to 0 f of 1 plus x divided by f of 1 whole power 1 by x. We have to evaluate limit extending to 0 f of 1 plus x divided by f of 1 whole power 1 by x. Now, let us see, as x tends to 0, 1 plus x tends to 1. So, this is f of 1 by f of 1, which is 1. This quantity it is tending to 1. And as x tends to 0, 1 by x tends to infinity. So, this is 1 power infinity form. This question is direct question on 1 power infinity form. And in 1 power infinity form, we know limit extending to a f of x power g of x. Whenever it is 1 power infinity form, we write this limit as e power limit extending to a f of x minus 1 into g of x. In a 1 power infinity form, limit extending to a f of x power g of x, we will always be writing it as e power limit extending to a f of x minus 1 into g of x. So, let us do the same thing here. This limit, it will be limit extending to 0 f of x, the base, minus 1, that is f of 1 plus x divided by f of 1 minus 1 into g of x is 1 by x. G of x is 1 by x. So, now our target is to evaluate this limit. For that, let us use the given information. F of 1 is 3. So, this we can replace and write it as 3. Now, when we are taking the LCM, it is f of 1 plus x minus 3 divided by 3 into 1 by x. Directly we can write it here 3x. Now, as x tends to 0, this is f of 1, which is 3, minus 3, 0, by x also tends to 0, this is a 0 by 0 form. So, to evaluate this limit, let us apply L'Hospital rule. This will be limit extending to 0, differentiate numerator f dash of 1 plus x, derivative of minus 3 is 0, divided by 3. So, as x tends to 0, f dash of 1 is also given to be 6. So, this limit, it will be e power f dash of 1 plus x, as x tends to 0 is 6, 6 by 3 is 2. So, this limit is 2. Our answer will be e square, or the option is C. Answer is e square and the option is C. Next question. If f of x is equal to sin x whenever x is not equal to n pi and 2 otherwise, and g of x is given as g of x is equal to x square plus 1 when x is not equal to 0, or 2, 2 when x is equal to 0, 4 when x is equal to 2, then we have to evaluate limit extending to 0 g of f of x. In this question, f of x is given as sin x when x is of form n pi, where n is an integer, 2 when x is not an integral multiple of pi, and g of x is given as x square plus 1 when x is not 0 or 2, 2 when x is 0, and 4 when x is 2. F of x and g of x are defined as sin x when x is not an integral multiple of pi, 2 when x is not an integral multiple of pi, and g of x is defined as x square plus 1 when x is not 0 or 2, 2 when x is 0, and 4 when x is 2. And we are asked to evaluate limit extending to 0 g of f of x. We are asked to evaluate limit extending to 0 g of f of x. So, to evaluate this limit, we have to evaluate left hand limit and right hand limit separately. Let us start the question by evaluating left hand limit. As x tends to 0 minus, that is when x is slightly less than 0, we are asked to find the value of g of f of x. X is given to be slightly less than 0. So, when x is slightly less than 0, x will not be an integral multiple of pi. X will be an integral multiple of pi when x is exactly 0. But here x is slightly less than 0, so it will fall into the category of x not being n pi. And whenever x is not n pi, f of x is a constant function 2. So, we can replace f of x and write 2 here. So, left hand limit will be limit extending to 0 minus g of 2, and g of 2 we all know it is 4. So, left hand limit is 4. Now, let us evaluate right hand limit. Limit extending to 0 plus g of f of x, g of f of x as extends to 0 plus. When x is tending to 0 plus, x is slightly greater than 0. X is slightly greater than 0. That means x is again not an integral multiple of pi. So, f of x is again 2. It is a constant function, 2 in the neighborhood of 0. So, we can write it as 2. And g of 2 we know again it is 4. So, both left hand limit as well as right hand limit are equal to 4. So, the limit exists and is equal to 4. So, the option is B. Next question, the function f of x is equal to sin pi x by 2 if x is less than 1 and mod 2x minus 3 into step x if x is greater than or equal to 1. We have to check whether it is option A continuous at x equal to 1, B differentiable at x equal to 1, C is continuous but not differentiable at x equal to 1. So, for the function f of x is equal to sin pi x by 2 if x is less than 1, mod 2x minus 3 into step x if x is greater than or equal to 1. We have to check whether the function is continuous at x equal to 1 or differentiable at x equal to 1, or option C is continuous but not differentiable at x equal to 1. So, let us first check the continuity. For continuity at 1, left hand limit at 1 should be same as right hand limit at 1 should be same as functional value at 1. So, let us first evaluate what is functional value at 1, f of 1. Whenever x is equal to 1, f of x is given by this definition. Step of x, step of 1 will be 1, mod 2x minus 3, 2 minus 3 is minus 1 with mod is 1. So, f of 1 is 1. Let us evaluate right hand limit at 1, f of 1 plus. Whenever x is slightly greater than 1, f of x is given by this definition. F of x is given by mod 2x minus 3 into step x. Now, x is slightly greater than 1, and whenever x is slightly greater than 1, integral part of x is going to be 1. X is slightly greater than 1, so integral part of x is 1, and 2 minus 3 is minus 1 and mod is 1. So, again this is 1 into 1, 1. So, right hand limit is 1 and is same as function value. Let us also evaluate left hand limit, f of 1 minus, that is x is slightly less than 1, and whenever x is less than 1, function is given by sine of pi x by 2. So, we have to evaluate limit extending to 1 minus sine of pi x by 2, that is we have to evaluate the value of sine pi x by 2 when x is slightly less than 1. So, if x is slightly less than 1, pi x by 2 will be about pi by 2 and sine of pi by 2 is about 1. So, we can see right hand limit, left hand limit and function value are all equal and equal to 1. So, the function is continuous at x equal to 1. Now, let us check the differentiability also. For differentiability, we have to evaluate left hand derivative at 1, and left hand derivative at 1 is given by limit x tending to 1 minus f of x minus f of 1. F of 1 we have seen it is equal to 1 divided by x minus 1. So, left hand derivative f dash of 1 minus is given by limit x tending to 1 minus f of x minus 1 divided by x minus 1. As x tends to 1 minus, x is slightly less than 1, and when x is slightly less than 1, f of x is given by sin pi x by 2. When x is slightly less than 1, f of x is given by sin pi x by 2. So, this limit is going to be limit x tending to 1 minus sin pi x by 2 minus 1 divided by x minus 1. This is a 0 by 0 form. We can evaluate it by simple L'Hospital rule. Derivative of sin pi x by 2 is pi by 2 cos pi x by 2. Derivative of x is 1, and as x tends to 1, cos pi x by 2 tends to 0. So, this limit it will be 0. Let us evaluate by L'Hospital rule. Limit extending to 1 minus derivative of sin pi x by 2 is cos pi x by 2 into pi by 2 minus derivative of minus 1 is 0 divided by derivative of x is 1, and as x tends to 1 minus cos pi x by 2 is 0. So, this limit is going to be 0. So, we can say left hand derivative is 0. Left hand derivative we got it to be 0. Let us look at right hand derivative at 1. Right hand derivative is given by limit x tending to 1 plus f of x minus f of 1. F of 1 we have seen it is equal to 1 divided by x minus 1. And as x tends to 1 plus, x is slightly more than 1, and when x is slightly more than 1, f of x is given by this definition mod 2x minus 3 into step x. So, we have to evaluate limit extending to 1 plus mod 2x minus 3 into step x minus 1 divided by x minus 1. As x tends to 1 plus, that is x is slightly greater than 1, when x is slightly greater than 1, integral part of x is going to be 1. So, integral part of x we can replace it by 1. When x is slightly greater than 1, 2x minus 3 is about minus 1, which is negative. and modulus of a negative number is minus of this number. So, modulus of 2x minus 3, because 2x minus 3 is negative, will be 3 minus 2x, or minus of 2x minus 3. 3 minus 2x. This 3 minus 1 becomes 2. 2 we can take common. 1 minus x and 1 minus x gets cancelled. So, this limit, it is equal to minus 2. Right hand derivative, it is equal to minus 2. So, the function is continuous yet x is equal to 1, but not differentiable at x equal to 1. So, the more appropriate option is answer C.